Yeah.
Okay. Hi, so nice to be back here where many of you know that I actually was here for over a decade working with Lindsay Farrer in genetic epidemiology, and with some of you familiar faces. It's wonderful to see you and wonderful to be back. I have very happy memories of working here. The thesis I'm going to talk about today is basically this, that we have been remiss in not bringing genomics into the day-to-day care of patients much sooner, much faster, much more comprehensively than we have done, and that we should redress that quickly and thoroughly. And the theme throughout this talk is that I've tried to bring some evidence base to the disclosure of genetic information and essentially demystify some of the myths that have surrounded this and have prevented us from using it. My research is supported almost entirely by NIH, but I've also benefited from these other sources of funding. I am a paid consultant to those three companies, and I've co-founded two companies, as you can see there. So some of you work in day-to-day medical genetics, and you know that we basically in genetics, we diagnose rare conditions, we do some preconception screening. Our day bread and butter is to talk to pre-symptomatic families, to follow up on newborn screening, to do some prenatal screening for aneuploidy, and the vast world of targeted therapies for cancer, which I'm very far away from. And you know that there are these new areas that are coming: population screening, newborn sequencing, polygenic risk scores, prenatal sequencing, not just NIPT, expanded carrier screening, and expanded pharmacogenomics. And all this is leading, we all think, to a world where we can gene edit and use gene and cell therapies to correct these genetic conditions, and where we integrate this layer of genomics in with these multiple other layers of big data so that we can create multiple huge data profiles of patients. And so this is kind of, these slides haven't changed much in about 10 years. Now, in particular, for 30 years, I found references to the idea that we might want to take this DNA blueprint and use it at the beginning of life. So you can see there are quotes there from various groups and individuals between 1992 and 2013. And my friend Wally Gilbert, Nobel Prize laureate for the very first technology for sequencing DNA, has told me that, in fact, they were talking about this in the 1980s. So this goes back a long time, and yet we haven't done it. While at the same time, there's been a huge influx and recognition of new genetic disorders, the frequency of genetic disorders, the variation in genetic disorders, and relevant to my host today in pharmacology, and this is my only pharmacology slide, there are all sorts of new medications coming out from pharma that can actually change the genetic code or can replace enzymes that are missing. I lump these all under gene and cell therapies. And there's like $1 trillion of investment in gene and cell therapies now. And probably 10% of genetic conditions may be treatable today, but many, many more very soon. So why is it that we have been so slow to bring genomics into day-to-day medical care? Well, there's a concern that genetic information can cause irreparable psychological distress. There's lots of concerns about privacy and discrimination. There's a notion that neither participants, patients, or even providers are going to know what to do with it. And there is a concern that harms will outweigh harms and the costs will outweigh the benefits. And I basically worked in a program that we've called Genomes 2, with the number 2 people, for the last 15 or so years, starting here at BU, to try to address some of these questions. Now, as many of you know, I was in Alzheimer's disease when I was here, working with Lindsay on genetic epidemiology of Alzheimer's disease. And I got interested in ApoE, which was very hot in the time I came out. And I wrote a grant, the first grant, it turns out, to disclose a genetic predisposition called the REVEAL study, Risk Evaluation and Education for Alzheimer's Disease. And for 4 separate NIH cycles, we stretched that baby over about 15 years. All I did was disclose ApoE to volunteers who wanted to learn about it. And there's so much to say here. We published about 47 papers on this, including the sort of New England Journal flagship. But I'm not going to dwell on that except to say we debunked a lot of concerns about catastrophic distress, what people would do with the information, how it would be used, how they would share it. Did you need genetic counselors? Could it be disclosed by brochure, by telephone, numeric disclosure versus categorical disclosure, you name it. It got me really interested in genetics and in what I thought was the kind of coming tsunami of genetic disclosure. There's just one problem. I only knew about one gene. So I did a crazy thing. After becoming a full professor here in neurology, I went back to residency and did a second residency in medical genetics. And that was my wife was not very happy about that, but I was on fire. My first residency in neurology was great. But this, I really wanted to learn about. I was that kid in the front row who was like, wait, I don't understand this. And it's just nothing but pure joy to learn this material because I was so excited about it. And so I went from one gene basically to all of them by way of the explosion in direct-to-consumer genetic testing. I wrote the first grant on DTC, and we studied 23andMe and another company. And we wrote a lot about how consumers were understanding the health-related genetic information they were getting from 23andMe and this other company called Pathway, and whether or not it was really influencing their health behaviors. Some very interesting observations there. A lot of interesting things about what they thought their risk was, how the information was presented. Did it change their risk perception? Was that risk perception elastic and it came back? And again, what exactly did they do medically and behaviorally in light of genetic information? And then finally went to the whole genome, because the whole residency I'd been asking my teachers, why aren't we genome sequencing everybody? And they were saying, now, bide your time. So I wrote a grant called the MedSeq Project, where we whole genome sequenced healthy adults for the first time in history. This was before Craig Venter did his, before Mike Snyder did theirs. And we demonstrated that, if you can believe it, close to 15 to 20%, and conservatively 10 to 15%, but in some series 20%, of all of us, all of you, are carrying a monogenic disease risk. We're not talking about ApoE, we're not talking about array-based polygenic risk scores. We're talking about a monogenic disease risk, a pathogenic or likely pathogenic variant. At least 10% of you are carrying a mutation of that, and you don't know it. Almost all of us are carrying recessive mutations that are, of course, important for reproductive health. About 80% of us have an atypical response to at least one category of medications. It won't necessarily be one we see in our lifetime, but it's there. And more we realize the more polygenic risk scores we do, there are at least 50% of us who are in the top 5 percentile of risk on polygenic risk scores, which roughly translates into the kind of penetrance that you get with most single gene monogenic disorders, about an odds ratio of about 4. So this is actually quite a lot of genetic risk that's out there. And again, the question is, why aren't we looking for this? Why aren't we adding this to the armamentarium of probabilistic and predictive? So I'm going to skip ahead a few years, because the most interesting thing we've been doing for the last 10 years is a project we call the BabySeq project. This was the first project in the world to comprehensively sequence healthy infants. And we've grown this from a single site to about 10 recruitment sites around the country now, and we are hoping to grow it further. But we basically started with an almost inconceivable number of genes. First, we started with about 1,000 genes, and we selected them for disease gene validity. We selected them for age of onset in children and for penetrance. But then we basically said, let's just select genes for gene disease validity. In other words, we're only going to include genes that have a strong association to the disease in question. But we're not going to worry about penetrance because penetrance is basically unknown for most of these. We're not going to worry about adult onset because this might be the only time a child ever gets to learn. And we're not going to worry about treatability because what's not treatable today is likely to be treatable tomorrow. So we increased this initial list of about 1,000 genes to what we have done for most of BabySeq, which is 4,299 genes. And as I said, the disease validity is the most important component of that, but we're only looking at pathogenic and likely pathogenic variants, not variants of uncertain significance. We're not worried too much about age of onset, and we're not worried too much about penetrance. These are in a lot of different medical specialties, as you can see there, which is kind of one of the problems because these get pigeonholed into specific medical specialties. Many of them are rare, some of them are ultra rare. And we sequenced the first child on April, or at least we enrolled the first child on April 22nd, 2015. And to our knowledge, believe it or not, this was the first child in the world to be enrolled in a specific research protocol for comprehensive genome sequencing. Now, let me skip to really the lessons learned throughout all of these studies, and I hope this will be the most interesting part of the talk. First of all, indication-based testing, diagnostic testing, is fundamentally different than screening. Those of you who I've known from public health here at BU or have a public health background know this intuitively, but a lot of clinicians really don't process this. A few years ago, I created this diagram to try to illustrate that. So in diagnostic space, you've got a child in front of you with a mysterious disorder. You do a whole genome sequence these days. You're going to look for the genes with definitive, strong, and even moderate disease validity. You might even go into no evidence reported because this family might become sort of a single family that helps you identify a brand new gene. You're going to look not only at pathogenic and likely pathogenic variants, but you're going to move into variants of uncertain significance on the bottom there because, well, you're not 100% sure if there's a new variant that might be pathogenic that isn't already in ClinVar or somewhere else. And you're not going to worry about clinical actionability at all because you're trying to make a molecular diagnosis on that child in front of you. So the search space, if you will, for a diagnostic genome, this three-dimensional search space I've created with these three axes, is much larger. When you're saying we're gonna look at everybody in this room or everybody on this campus or everybody in the country, and we want to look for pathogenic variants in actionable conditions, we want to shrink that search space. We only really want to look at genes that are definitively associated with the disease. We really only want to look with genes that are pathogenic and likely pathogenic. The molecular geneticists kind of define this as 90% chance that it's going to be deleterious. And we certainly want to prioritize those conditions which are actionable in some form. Though, as we talked about with the students earlier today, actionable means different things to different people. But that being itself, this is the conceptual search space for proactive genome sequencing. A couple of lessons learned. Kind of makes sense. The more genes you look for, the more you find. So there's something called the CDC Tier 1. Have you guys heard of that? Which is sort of a descendant of Muir Khoury's work at the CDC, where 10 genes or so associated with breast and ovarian cancer, Lynch syndrome, and familial hypercholesterolemia were kind of considered the most treatable of the genetic conditions that are likely to be out there. If you just take those 10 genes, you are going to find it in 1 to 2% of the general population. Now let's just stop there and think about that for a second. 300 million people in the United States, that's 3 to 6 million people who are carrying a well-established mutation where recognition could meaningfully improve their health and lifespan. Or if you go a little farther, we created a list for the American College of Medical Genetics, first with 59 genes, and today it has about 81. And you can see that that increases the percentage. These are all considered, by consensus, treatable conditions. So if you look for those, you find between 2 and 5%. That 2.7% comes directly out of the Framingham Heart Study, where we looked for the original 59 genes and found them in 2.7%. If you go a little farther, some commercial companies have created panels with even more genes that are considered treatable, such as Invitae. The percentage goes up. And in our MedSeq, BabySeq, and MilSeq studies, where we looked at 5,000 to 6,000 genes, we find 10 to 20%. So it kind of makes sense, right? The more genes you look for, the more people you find who are carrying that. You can make a choice about this. If I were you, I would not walk, I would run to find a way to get yourself tested for at least the CDC Tier 1, no matter what your age, because you want to know if you have one of those conditions. Sequencing is easy, interpretation is hard. Sequencing costs per se have come down. You can get a whole genome in a CAP-CLIA environment scale for $300-400, maybe less if you go to one of the new companies. It's a little bit more if you go with long read technology. But the interpretation is still a somewhat semi-automated process. So not to dwell on this, but we start off with about 5 million variants, right? Each of us has about 5 million variants. You can take that through automated filters, very quickly get down to a couple hundred. But then you're kind of looking in the literature, you're looking in your own database, you're trying to exclude things, you're trying to look for missense variants in particular genes, and you're running into a few novel loss of function genes and disease-associated variants and disease-associated genes, and you're worrying about those. So when you write your final report, it's still a human endeavor. That's what's slowing down the genetic revolution. Recruitment, however, to research studies, or maybe even in your clinic, depends on how you frame this. In our first BabySeq study, we said we would like to sequence your brand new baby. Here's a 22-page consent form. You could have devastating psychological distress. You might find out something that's horrible in your child that's completely untreatable that might lead to death. You might have all sorts of privacy invasions, including non-paternity, and the baby could grow up in an uncertain future where insurance could be, they could lose their insurance based on this. Not surprisingly, people were not enthused about that. But if you do it like most medical tests, you maybe touch on some of these things in a more balanced way, the percentage of people who agree enthusiastically to have their genome analyzed goes way up. So in our very first BabySeq studies, we found that people were very interested. 70% of people who completed surveys on basically your basic interest were super interested. But when we used that 22-page consent form, most people declined, and we ended up with about 10% of the total population enrolling in the study. It's quite interesting because the people who are resistant to genetics interpreted that paper as, you see, nobody wants it. But it turns out that by the time we did BabySeq 2, we reframed the consent form with all those points touched on, but in a much more balanced way. Now you can see that 28% enrolled right away, a larger number were undecided, and some have contacted us later. And that is across the board, whether it's white, Black, Hispanic, Latino, or other ethnicities. So, and then in the Guardian study in New York State, 97% of people basically said yes, because their consent form was so for want of a better word, friendly. And when people do decline, at least in our hands, there's a variety of things, including I just don't want to participate in research. So all of these will be familiar to you if you imagine yourself as a new parent. Somebody walks in the room, says, hey, do you want to participate in this research study with your brand new little baby? And there were all these reasons they were given. Now, severe distress is where all this started. There was just a perception, and I think it started historically because of some of the earliest genes to be disclosed to people were Huntington's, which of course is a devastating death sentence, and BRCA1, which was very charged because of the actionability, can often involve life-changing surgeries, prophylactic surgeries. So there was a lot of distress in these. I don't mean to minimize those at all. But there's a vast array of probabilistic genetic information, which has kind of gotten captured by that construct. And it turns out that if you actually test people's level of distress on validated scales, which we did in MedSeq, in the adults, there was no increase in anxiety, whether it was for the people who were sequenced versus the people who were not sequenced at all, or the people who were sequenced and did not find out anything versus the people who found out that they had a monogenic disease risk. There was no meaningful difference in distress. And this has been shown over and over and over again by multiple groups. I know it's a little counterintuitive, but it's true. They're simply because people self-select. This isn't quite the same as the diagnostic scenario where you have a sick child or you yourself are ill and somebody kind of imposes genetic testing on you. And sometimes the results are really upsetting. This is, do you want to learn this? And when people know that they're going to react poorly, they decline. So when they say yes, they are already self-selecting. This is also true in the parents of our BabySeq patients. So randomized clinical trial, half of them got sequenced, half of them didn't. And the third bar there in the bar graph are the children who were carrying a positive mutation, or the parents of the children who were carrying a positive mutation. Take-home message is the same. No meaningful distress, certainly no catastrophic distress. Now, another lesson learned is that monogenic risk variants are common, and they frequently reveal undiagnosed or misdiagnosed cases. So we've come at this in two ways. In the BabySeq project, for example, in BabySeq 1, we found these results. In many, when we examined the children, there was absolutely no phenotype yet. It might develop in the future, it might not. In some of them where there was no phenotype, but there was an unrevealed family history that only came to light as a result of the finding the mutation. And in about a third of the positives, or a quarter of the positives, we examined the child and found a previously unrecognized clinical feature of the underlying disease. Now just imagine that for a second. This is an unselected population of healthy children, basically healthy children. They're not referred to us because they're ill. We find in a quarter of this small sample size, through the prism of a genetic finding, an undiagnosed or misdiagnosed clinical syndrome in a quarter of them. Imagine any other diagnostic test on the planet, any other screening test on the planet that would give you that kind of information that frequently. It's inconceivable. So we didn't just take this first cohort, we did it again. We did it in BabySeq 2 with a much more multi-ethnic population. And sure enough, the exact same pattern. Now, these are small sample sizes. We've only done 1,000 families in BabySeq, whereas other groups have done many more. But we've looked at far more genes, and because of our small sample size, we can go back to those babies and explore in exquisite detail, biochemically, clinically, radiologically, if they have features of the disease in question. Another lesson learned is that cost or value precedes cost savings. And by that I mean there's a narrative here, right? That, yeah, look, we should sequence everybody because we're going to save money through prevention. Well, maybe that will be true someday, but that's not going to be true for a long, long time. Sequencing is still expensive. All the workup for people at risk is expensive. We're going to lose money for a long, long time on this. But how much money are we going to lose? We started to actually try to understand that first in BabySeq, where these were the mutation positive cases. Those were the controls over there. And you can see that the amount of money spent was in the 10 months following, sorry, in the 6 months following disclosure, doesn't look very different. And we looked at that in different ways. This is without factoring in the cost of the sequencing and interpretation. And sure enough, the patients who get sequenced do have a higher spend in terms of healthcare visits, medications, and so forth, but it's not a lot higher. So for the first time, we're trying to quantify what this is going to mean on a societal basis to do this. And you can see that even among the people sequenced, the ones who didn't have a monogenic disease risk versus the ones who did have a monogenic disease risk, it's slightly higher, but it's not statistically significantly different. So there's a lot, bottom line is there's a lot of noise in healthcare spending, whether it's a baby or an adult. Healthcare spending's all over the place. If I go out and slip on that part of the sidewalk where you told me not to walk because there's ice falling, I walked on it. And I was looking up for ice falling on me. But if ice had fallen on me and done me some damage and I rolled into the emergency room with that, that's going to blow my healthcare spending off the map. And so there's just so much noise in the healthcare spend that, at least to our mapping so far, the follow-up costs are not terribly disruptive. Now, not everything is treatable, but almost everything is actionable. And what I mean by that? Well, if you take a neurodevelopmental condition like severe autism, what we used to call mental retardation in some form, or intellectual disability today, there's not a pill, there's not a surgery, there's not something we can cure that with for the most part. But there is well-accepted interventions that the earlier you enrich that child's environment, the more functional that child will be. And if you know that child is carrying a mutation for that early, you can start that early. Is that actionable? I'd say yes. Is it treatable? I'm not sure I'd say that. It turns out that there is a semi-quantitative measure of disease actionability where you kind of give a somewhat subjective score on disease penetrance, disease severity, the tolerability of the intervention, and the efficacy. So for example, with Marfan syndrome, it's a great example because it can be pretty severe. You can burst your aorta, that's not good. It's highly penetrant. There is a very effective intervention. You just surveil for the aortic dilation. And surgery is pretty tolerable. So you would give that a full diamond shape, whereas let's take our Huntington's disease, very severe, highly penetrant, no real effective intervention yet. And that would have a shape like this. So if you keep those shapes in mind, I'll show you all the conditions that we found on BabySeq. So here are all the conditions we found on BabySeq, and they more closely resemble the diamond than the triangle. And when you score them on this scoring scale that I did not make up, but ClinVar made up, they are all over the threshold of actionability. Who knew? So I'm not saying this is gospel, but it's certainly interesting to think that the majority, if not the all of them, are actually in some fashion actionable. Now, I think it helps to actually hear from some of the mothers of babies who found something, both treatable and untreatable. So here's a couple of just very brief snippets of video.
Finding out that your newborn has a heart problem of all things is absolutely terrifying. But knowing that we could be proactive gave us some peace of mind, that we were doing everything we could do instead of being surprised down the road.
Now, that was an elastin mutation, can be associated with an aortic narrowing. And in fact, when this baby had an echocardiogram to follow up on the genetic test, the aorta was abnormally narrowed. So this baby has been surveilled over the years. And interestingly, way after this was shot, the baby's aorta has grown at a normal rate. It no longer is dilated. So you could say, well, you see, you didn't even need to do that. But if that dilation had gotten worse, if that constriction had gotten worse, and that baby had started fainting on the playground, you'd have had an immediate place to go to for relief rather than taking time. This next one is a child who had a partial biotinidase deficiency.
We give her a daily vitamin to treat her enzyme deficiency. We had to get creative at first, but now it's part of our routine. And this why we started the conditions before there were any symptoms.
Now, this was one severely pathogenic mutation in biotinidase deficiency in biotin, and a leaky mutation on the other side, such that the enzyme level wasn't 50%, which you'd expect with a typical heterozygote, but was more like 30, 40%. Certainly didn't have the full syndrome, right, with severe intellectual disability, seizures, skin and hair problems. But how do we know that that degree of enzyme deficiency might not influence the child's brain development? Maybe it would be 15 IQ points different. Well, in this case, the solution was simple, cheap, and harmless, a biotin supplement. So even though there's some ambiguity about the treatment, this child was treated and grateful. And we didn't try to sugarcoat it. We told her the truth. We don't know if this partial biotinidase deficiency may influence your child's cognitive growth or not, but here's something to be on the safe side, and they were very happy with that.
It turns out that I ultimately was carrying a mutation. I had risk-reducing and ultimately life-saving surgery, and I believe it was the right decision so I could be present for my son.
This little baby was a boy who had a BRCA2 mutation. Now, almost all the ethicists in the pediatric space would say, under no circumstances should you test a child for an adult onset cancer because you don't know if that child would want that knowledge, and you're taking away the right not to know. I respect that position, but I do disagree with it because in this case, the child was a way of finding out, and the only way of finding out that this mutation was running through this family. This mother had risk-reducing surgery, and as have several others in our study, and indeed will be able to live longer to be there as a mother for that child. Another lesson learned is that penetrance depends on your definition of phenotype. And so, for example, here are the infants in BabySeq 1 that were all carrying mutations, the entire row, and there's the genes that the mutations were in. Only the ones in orange actually had clinical features of the condition. But these were mostly dominant conditions, and when we checked their parents, we found that in some, the parents had, in this case, cardiac abnormalities, which were now clearly attributable to the TTN mutation, but had not been known before. So are we measuring penetrance on an individual basis, on a family basis? Oh, and by the way, what happens when you start testing these individuals with biochemically or radiologically? If you find a very clear-cut abnormality, but they're not symptomatic yet, is that penetrance? I would say yes, but most geneticists would say no. So really, we have to rethink what we mean by penetrance. Are we talking about penetrance at the individual level at one moment in time, over a lifetime, over a family structure, and over what kind of phenotype? And then, as I mentioned, even 3 of these parents who just by chance happened to be women, all found out they had a genetic cancer predisposition. All 3 of them underwent risk-reducing surgeries. So genomic screening is likely to evolve differently from public health laboratory-based newborn sequencing. So it's very tempting to say, wow, we've got this system in the United States, right, where we do a heel stick on every baby born, right? All 3.4 million babies in the United States, almost 100% of them, excuse me, have a heel stick, and they're tested in a public health laboratory, mostly biochemically, for 30 to 60 conditions, right? That's our newborn screening system. Well, you got the blood spot, you got the DNA, let's just sequence that blood spot. And I think that is going to happen. And I'll tell you about our study Beacons in a moment where we're testing that. But I also think that that's not the only point in time that genetic information could help a child. I mean, you've got to draw the line somewhere in a public health system. You probably want the conditions that are most urgent. You probably want the conditions that are the earliest in life. You definitely don't want to be testing all American children for adult onset conditions. So where do you draw the line? Well, I don't know, but you draw the line somewhere. Whereas in the lifetime of a child, at age 1, 2, 5, 9, 14, genetic knowledge is going to continue to evolve. New treatments are going to continue to be available. So the vision for genome-enhanced ongoing medical care is that you use genomic information throughout the lifespan, depending on where you are. And I made this graphic in which you do a certain amount of testing on a child. You may or may not find a specific mutation when you look as a child, but then you continue to analyze maybe even that same genome over and over again in light of new scientific information, new treatments as the child grows up, and you have this whole genome-infused medical care system. So I really see genomic screening of children going in two directions. One, which will stick with the conventional newborn screening operation, and one which will move into pediatric practice. So let's talk about the one with the newborn screening, because that's the one your mind goes to. Turns out that NIH finally, there have been a number of pilot studies in this in various states after Baby-Seq came out, but there had never been a multi-state initiative until NIH launched a collaboratory competition, and I put together a team that won it, and we call our new thing Beacons, Building Evidence and Collaboration for Genomics in Nationwide Newborn Screening. And in this, we have selected 7 states, and we are using a team made up of all these groups that are going to be choosing, we've already chosen Oregon, Texas, Minnesota, Iowa, New York, South Carolina, and Puerto Rico as the 7 states, territory in case of Puerto Rico, where we're going to be testing the idea of using the blood spot in order to do whole genome sequencing and return 746 genes for 777 conditions, all of which are treatable in the first year of life. I won't go through the whole workflow there, but this is the team after we found out that we won. And this is Robert Guthrie's daughter, Patty. And those of you in this space know that the Guthrie spot, Robert Guthrie is the father of newborn screening. And she was kind enough to come to our kickoff meeting and help celebrate with us when we won this award. I want to end up, if you're interested in this area, by telling you about a new organization that I co-founded called the International Consortium on Newborn Sequencing. It started off with just 6 groups, because that's all there were in the world who were doing it. And then it's grown, if you can imagine, it's grown to 60 programs globally with over 500 members from 54 countries, a bunch of subcommittees working on projects. And the 2026 meeting is here in Boston in October. And this is the best deal you can possibly do. You can join icons for a very low membership fee. We started with Baby-Seq here in Boston. Baby-Seq was the only program in the world for a while. And then as you can see, programs have sprouted up all over the world. And they all have cute names and cute logos. The purpose of the organization is to try to do some data harmonization and understand how we can do this scientifically and policy-wise throughout the world. There are subcommittees if you're interested in participating. This is such a young organization that if you are interested, you can have a big impact. So please volunteer in order to join this. Yeah, the annual meeting is October 7th and 8th. If you have your phones and you want to pull them out right now, you can take a picture of this QR code, which will take you directly to the membership page where you can sign up. Come on, get your phones out. And you can become a member of ICONS and you will not regret it. All right. I'm going to stop in a minute, and I want to leave time because there's always lively conversation and discussion when I talk about these things. But I'll finish by saying that you can find our work at genomes2people.org. You can follow us on X, on Instagram, and you can find some of our work on these websites. I'd be delighted to send anybody a copy of these slides if they're interested, and be delighted to, if you're interested in working with us, we have students and fellows who do rotations with us, both summer and long-term. And by all reports, they have a pretty good time. We have a really fun group. We do a lot of fun things together. So that's the talk. Why don't we open it up for conversation? Yes, sir.
Identical twin. One can get two for the price of one. What are the benefits?
Well, I think it's such a cool thing to be an identical twin. You are an identical twin? Interestingly, from the framework of typical genetics, it's mostly people have worried about if I test one twin and I find out something scary, we have inadvertently disclosed it to the other twin if they talk. So that's been the framing of most of the conversations in clinical genetics about twins. But then scientifically, it's so interesting because identical twins can have the same mutation, but get the disease at entirely different ages. Or one can get the disease in question more severely than the other gets the disease, which just points to the fact that genetics it's a foundation, but it's not the defining feature of whether you get a disease or how severe you get a disease. And we know that other genes are contributing. In your case, those would be the same, but we also know that there are environmental factors, epigenetic factors that influence that as well. So there's probably people in genetic epidemiology who know more about twin studies here than I do, but it's a fascinating area, and congratulations on being a twin.
So I want to Patrick, that my identical twin brother and I got cataracts at 3 months.
Exactly the same time. How fascinating. Yeah. Well, back when I was doing Alzheimer's disease, there were identical twins, even who had the monogenic disease risk, so they were definitely going to get it, but they got it at very different ages, which was always puzzling. Yeah.
I was very interested. You mentioned sequencing is easy, but interpretation is hard. So how sophisticated is variant calling getting, where you're going beyond just looking at SNPs, catching deletions or transposed element?
Yeah, thank you. So the sequencing is easy. The question is sort of how complicated is variant calling and interpretation. So I'm not an expert in the molecular genetics but I've learned a lot from the people I work with. And so the sequencing is sort of what I think of as what comes off the machine, just the digital letters. Now, the machines have added on some degree of variant calling. For example, the Illumina machines now have some degree of variant calling built in. But then Beyond variant calling, there is a layer of which of the variants that have been called are pathogenic and which are not. Some of those you can throw up against a known database like ClinVar, and it's pretty easy. But there's always a subset of those that are harder because either they're not in the database or they're in the database with conflicting interpretations. And that's what tends to grind the automation to a halt. And if you're willing to throw those out, you can do interpretation pretty automatically. And that's what some of these companies that are purely informatics oriented are doing. But they make card-carrying geneticists uneasy because there's definitely pathogenic variants in there that are getting missed. They're novel, or they're super rare, or they are controversial, or they have been shown to be pathogenic, but they're not yet updated in the database. I mean, we get really obsessive compulsive about this. So depending on your degree of tolerance for misinterpretation, you can do it faster or it takes longer. Yes, ma'am.
You talk almost primarily about sequence. So is there an effort to kind of introduce information about non-coding variants that might have?
Thanks. The question is about introducing non-coding variants, and there are a lot of people working on that. To my knowledge, in germline genomics, so not setting aside the cancer space, the somatic space, in germline genomics, all of us, there are very few relevant promoter enhancers or other non-coding variations. There are certainly canonical splice site abnormalities that are known. And of course, also pursuant to your question, there are a lot of structural variation, which in between the small indels and the very large structural variants have not been picked up and interpreted as much, that are kind of getting solved little by little through structural variant databases. But the kind of screening that I'm talking about is primarily restricted to the protein coding portion. So you could ask, well, couldn't it be done with much cheaper exome sequencing? And it could. It could. You would lose the ability to go back to it as rigorously, and you would lose some of the granularity of structural variation that's better with a whole genome. Yes, ma'am.
In the context of all this, anecdotally, just people just fear of finding an unknown, which I think you've done a good job of showing. It's not. Is not nearly as severe as their fear of changes to their health coverage, insurance coverage, things of that nature. So I'm wondering if this sort of two parts are kind of really integrate that problem, especially in this time of year, sexual state fluctuation, as well as like how does that get incorporated soft version of release for this time?
Yeah. It's a wonderful point, and it's about the fears of discrimination, particularly insurance discrimination, incorporated into this whole thing. And you're absolutely right. There's a huge concern about that. The Genetic Information Non-Discrimination Act of 2008 did cover that you cannot be discriminated against in the basis of your health insurance for any aspect of your genetic information, and your employer cannot discriminate against you. So it protects those two things, but it did not go as far as to protect life insurance, disability, and long-term care coverage. So theoretically, like with the rest of your medical history, a life insurer could learn that you carried a mutation and could increase your requirements for life insurance. That is true. That's been, in my opinion, that's been over-indexed on in comparison to the health benefits of genomics. So it's certainly true, but it hasn't been done much. And even if it were, it's not completely outside the pale of what they do already. They go look at your medical record, and if you have a strong family history, they may use that. If you have a abnormal blood test or high blood pressure, or you're a smoker, or you've had cancer, they'll certainly use that. So, okay, what's the worst case scenario here? You're carrying a mutation for a cancer predisposition gene, and instead of the base rate, you get an increased rate for life insurance. Now, pardon me? Or perhaps non-coverage. That's right. That's the worst case scenario. Okay. You also now have insight into a risk that can save your life. So it's really curious how we've elevated the risk of insurance discrimination, which is not great, compared to the risk of life-saving information. And in many cases, we've elevated that insurance discrimination risk above the medical value. I don't understand that. I think it taps into a great inchoate fear in this whole society because of our dysfunctional healthcare system, that our safety net may be taken away and we can't count on insurance, and people conflate life insurance and healthcare insurance. And, I think it ties into a whole bunch of sort of social, psychological things. It doesn't make sense to me in a rational sense. I don't mean to diminish it. Yeah, I don't mean to diminish the fear. Of course, it is fearful and people fear it. But if you sort of put those two on a scale, you kind of want to live. Yeah.
I have a question about the next step. Next step for adoption of frequency. What should make a convincing argument for the adoption? Do you agree with type of study that would make the like study the
Yeah, what kind of
what are you thinking?
Yeah, the reasons, so the question is what kind of convincing studies would kind of accelerate the adoption of newborn sequencing? Well, the reasons that people give are what you guys are all touching on. We really don't know the penetrance. If those of you with a baby today got your baby sequenced and you found a mutation for, let's say, a cardiac rhythm abnormality, sudden cardiac death, that's a really scary mutation to find. But we literally don't know if your baby has a 1% chance of dying, a 5% chance, or a 50% chance. We literally don't know. There's been no long-term population-based studies that came at it that way. So variable penetrance and uncertain penetrance is a huge thing. But think about it. How do you figure that out if you don't? It's kind of chicken and egg. You got to sequence them and follow them to get an inkling of the penetrance. The other is all sorts of questions about privacy discrimination, not just insurance-based, but particularly in historically marginalized populations where you have people who truly believe deep down that there is a high probability that if any government has or any biobank has your DNA, it can be used by law enforcement to frame you for a crime. So there's a whole set of fears in there that some are justified, some are unjustified, some are partially justified, but by the facts as I know them. But there's a whole universe of fears. So those need to be addressed. And the only way those are basically, and the third category, of course, is that the medical system is unprepared for the onslaught of risk. So those are the three big categories of obstacles as I see them. And the only way I can think of to overcome those is to collect the evidence for the penetrance and to get enough narratives of children whose lives are benefited to kind of overcome the fears about the other things. And then just like Doctors had to get used to x-rays. Doctor has had to get used to, non-psychiatrists had to get used to using antidepressants. I mean, there's a vast history of doctors who screamed, I don't want to do this. It's new. I don't want to learn it. Well, tough. This is coming, and they'll figure out a way to do it. AI is going to help a lot, frankly, because it's a very esoteric specialty. When you can look things up quickly, it's going to make a big difference. Yes. Yes, ma'am. 54 programs around the world. Yeah.
What phases play phase somebody in America? And what's the unexpected protocols? Is that some part where to either other parts?
Yeah. So the question's about all the countries around the world. So there are 54, maybe even 60 now, programs. There's quite a few in China, and probably the most absolute number of children have been sequenced in China. There's a bunch in Australia, a couple in Europe. The big one is the Generation study in the UK, which proposes to do 100,000. Their health minister is already, before the team even authorized this or weighed in, the health minister already said, we're going to do this for every child that's going to be born in the UK, which kind of shocked the team there. And there's a few from odd places like Puglia in Italy. Decided to do this for all babies and found a way to fund it. Who knew? Most of them are research based. In other words, they're funded either by the state, but they're framed as research projects, which are consented on top of the typically unconsented newborn screening. Though a number of mostly West Coast people have argued if you don't consent for PKU and you don't consent now for a single gene for spinal muscular atrophy, right? That's joined the recommended uniform screening panel. So every state in the United States now, without consent, tests for the SMA gene. What's the difference between testing for one gene and testing for 746 genes? Why are we bothering with consent? If by consensus we've agreed that these are treatable conditions, why don't we just do it? So I'm not quite ready for that. Let me just get a couple more people first. Yeah.
Things, one now.
Beacons, yeah.
Yeah. So once you find a hit that's either treatable or actionable, I'm curious about the protocols, the approach with families, and then you provide the resources and referrals to give them data.
Yeah. It's a great question. Is what's sort of the downstream protocols once you find somebody with a mutation? And that's always been a question in these disclosure studies. Like when we did Framingham, same question. You find somebody with a mutation. What if they have no health insurance? What if they live in a rural area with no specialists around? What if? Well, what I've always argued, and thankfully IRBs have bought this, is that it's better to know and have an opportunity to travel or follow up or find assistance than not to know. So that argument has won the day most of the time, but it is a reasonable concern and it's a concern about equity. It's a concern about overwhelming the system. In Beacons, we address this very explicitly in that we are creating a 1 or 2 page sheet for all 746 or all 777 conditions, which will be available to the public health program to give to the pediatricians. And in case there's not a rare disease doctor in that specialty that's available to them, we have a 24/7 SWAT team of geneticists and genetic counselors here in Boston. We're not licensed in other states. We can't give care, but we can give advice to a pediatrician from Iowa who's in the middle of Iowa who feels unsupported. So I don't know if that's probably not a solution for the whole country, but for our Beacon study, it seemed to pass muster. Yes.
about the baby, so pathogenic or likely pathogenic patient you identify for future clinical trial enrollment. And for these, after they grow up and the leukemia goes out and they have a risk allele, look at the certain condition can be involved in the clinical project.
Yeah, is your question, can they be involved in clinical trials? Yes, and many people have pointed to that. I mean, it's fascinating when you create a list. It's very fascinating because there's some people who object to the things on the list. And then there's a lot of people who come out of the corners and say, but why didn't you put my thing on your list? And so you get it in both directions, which is fun. But anyway, a lot of people have asked us for beacons, hey, there's a clinical trial for this condition and you didn't put it on the beacons list. And the answer is we had to draw the line somewhere. We're not in the business, especially in a public health framing, we're not in the business of identifying children for clinical trials. That's one of the reasons I'm trying to, and honestly, this is just me. Nobody else is talking like this. So maybe it's just weird, but I'm trying to separate out into two pathways. What can be done in a true public health setting with universal testing, and what can be done if you integrated genomics into the ongoing life of a child in a pediatric practice. And in that second example, I think you could easily revisit the genome and incorporate clinical trial opportunities. And so that's one of the reasons why conceptually I try to separate those two threads, those two use cases or workflows. Yes?
Pricing product has more holistic healthcare system. And yeah, how's that going?
Thanks. The question's about pitching this in a country with a different structure of the healthcare system. As you might imagine, it's much more attractive in a single payer system because the costs are amortized over the entire life, whereas in our system, as you all know, gets split up into chunks based on your employment. And so the UK, unsurprisingly, is a leader from the world. Countries like Singapore, South Korea, some of the Gulf nations, Taiwan, are all very interested and rapidly trying to integrate this. A lot of Europe does have single payer systems, and even Canada. They're not so keen on it. And I think it's partly because they've, maybe it's some of the legacy of Nazi Germany and the surrounding sensitivity to eugenics. And the entire sort of philosophy of what eugenics was misused for. But mainstream European countries have not been fast followers to date. There are some projects there, but I'll never forget speaking early in the baby-seq stuff at Max Planck Institute, and they were absolutely horrified. I mean, they were polite because they were German, but they were really horrified. Yeah. I think we're past the time. I should probably let you go. Thank you very much for having me.
I with Dick Moss.
Oh, you did?
Yes,
Oh.
I spent 5 years.
It's such a
Yeah.
shame to lose him,
Yeah.
wasn't it? Oh my gosh. Yeah.
He passed away.
Yeah. What are you doing? What are you doing now?
I'm new in nephrology. Actually, I did the 5 years at the program of nephrology there.
Okay.
To genetics, and at that time, it's still with Boston.
Yeah.
Because they're like the other genetic people study DGAP, developmental genome analysis.
Mhm.
So I'm part of it.
And you're here now on the faculty
Yeah,
here?
yeah, and then.
Are you pretty happy here?
Good.
Okay, great. Thank you.
Okay, very
Hi.
nice. Thank you.
Hi, good to see you again. It's been a long time.
I did great.
Did you think I would go to this? This is pretty far from Alzheimer's disease, isn't it?
Oh, I know, but if you follow them long enough.
Exactly.
Yeah.
Study. No, day and night. Did you still, you didn't follow that? But some of that.
Doing all right, Mom. You still working? Yeah. Great idea. Yeah. University is, The job, just not, you know, to make a file out of that. Nice to see you. I'm sorry. I would love to talk about that. You saw that article that showed that there was some cultural variant that are Americans. I believe that.
Yeah.
So good to see you. Thanks for joining us on the weekend. Appreciate it. Thanks so much.
Yes, I think we're on just published in Australia, but it did targeted their sequencing published with I think and we're very innovation and trying to decrease screening for outcome and expedition. Well, is the CEO and considers that.
So let's, first of all, is it on Beacon's list?
No, thanks, so because
Just check
I
it.
think they're gonna say, I think they populate some data this time.
That's what we need to find out.
Yeah. And make sure.
These are the gases and it's very positive.
And I looked it up for, baby. They said, said both things, but I said, not sure if you're. But, severe emergency.
Okay. I will double check on the. Yes, so I'm just curious, are there?
Yeah, you're sort of, you mentioned. They are on why. Are there opportunities for the ways that you know that for young adults or people that have events? Australia, because I think this would be actual.
Well, we just got funded on
a different grant on adults to bring the CDC to them. And we were invited to add a change to this, and I think we can process and maybe one on the cancer team, but I don't recall like we don't be one of those. It's supposed to be a gathering of people. Is your argument that it indeed was treatable, or just that people shouldn't smoke?
Well, there'd be several, not smoking would be one thing, you say, that they change their belief. So lack of that, but then also, they're now, in case they're not, they have therapies that the gene editing is currently in clinical trials as are other therapies.
So almost all of these, yeah, almost all of these, I thought so, bigger spectrum of support here, but even so, all these things are very interpret for.
Yeah, so for adults, it can make an argument for augmentation, particularly in sites now with the augmentation mortality benefit. So with lung decline, emergency replacement therapy has enough retrospective now of the mortality benefit. So I would argue based on some different things that's as actionable as some of them.
As soon as you get into the social area, the specialists often see infection really where the generals.
Right.
So it becomes a really fascinating thing. The more deeply you go into a specialty, the more you. Let's see where Serpinati was on we did a bunch of emergencies. Did you see me in both states? Should. This paper was really aspirations to rank, thoroughly accustomed to rank each of 600 organizations there. Was on the see where they were.
They are one of the two most common areas.
Let me send you this.
I just wondering, so that's really for me to kind of go get it off the back of it. So then, if there are zombies or like I just makes you a little
So for screening adults, we would, you know, Jason Bessie, you know his name? So for screening adults, I'm MDI on this, but he's really leading that. Let me give you his, inputs.
Sure.
He'd be very happy to see that. I think it's Jay Vassy at, the same. Yep, Jay Vassy. All right, thank you. So of course, he's going to be leading. So that might be the best place to make an argument for this in short. It's not, definitely not on the essential. That's the next place. So they see US patients up to version 3.2, which is sort of the American College of Network St. John's list of shingle conditions. And they have a reason to they have to have a kind of a pretty clear secondary. Two B two, sure. So they got the US. Pretty sure it's not on there.
Okay.
But you can, in that article, they talk a lot about how to block. Or you go to the website, you just, there are ways to monitor your chips. Put it on the master list. It's secondary blocking. Everyone in the world sequences from the past. Recommend you equals the hard copy. It's not a problem. It's no problem. Realize that. Recommend also each year usually. That's the other question. Enjoy everybody. Let's make better than a lot of fun.